So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be going over how you can implement your own variety of the pulse algorithm in TensorFlow 2.0 using Python. Now before we get deeper into this, I do want to say that if you do enjoy this kind of content and want to see more of it, please do make sure to subscribe to the channel and turn on notifications. That way you actually know whenever I release a new video just like this one. Now today we're going to be covering some really fascinating stuff, but first of all, we have to take a little bit of a step back. What is pulse? Well, simply put, pulse is an algorithm that enables you to use GANs, or generative adversarial networks, in order to upscale images of really whatever. It's currently been applied to faces, but it could be applied to anything that a GAN has been trained to generate. But how exactly does Pulse use GANs to upscale pre-existing images? Well, let's take a look at that. But to understand that, we have to take another step back. How do GANs work in the first place? Now, simply put, generative adversarial networks work with two separate neural networks, a generator and a discriminator. The generator is trying to generate as realistic fakes as it can possibly create, and the discriminator is trying to determine whether a certain image was generated by the generator or was a genuine image from the data set. Now, as the discriminator becomes better and better, because it itself is a neural network and because that's differentiable, we can actually calculate gradients for the generator through the discriminator as a loss function. So we are essentially evolving the loss function for the generator alongside the generator itself. It's really fascinating stuff. But here's the thing, how does the generator work? I mean, the generator is just math. It can't just generate things out of nowhere. And that is where what's called a latent vector comes into play. Now, the latent vector is really interesting because what it does is it just defines a point in space. Now, not three-dimensional space as we know it, but rather 100-dimensional or 512-dimensional space. So way more dimensions than our minds can possibly fathom. But basically, you're defining a point in that space, and you're just finding a completely random point in that space. And you're telling the GAN, all right, here's the point. I want you to generate whatever data you have at that point. So kind of like how a regular neural network would take an image and map it to a feature space that is then classified by a linear classifier, in a similar way, the GAN has this sort of input manifold of all these different varieties of images, and you're just picking a random point in that space and telling it to generate whatever it is that you've trained it to generate, in this case, faces. Now, this GAN was already trained on what's known as the celeb-A, the celeb-aligned data set. It generates images of approximately 128 by 128 resolution. Now, this is definitely not the state-of-the-art trained version. That would take weeks to do on a cluster of GPU machines. However, it does generate realistic faces that we can use for the Pulse example today. Now, the way Pulse works itself is really interesting. Traditionally, to train a neural network, you calculate the gradient with respect to the network through a loss function. And so, for example, if we were training the discriminator, we would use something like the sigmoid cross entropy, or also known as binary cross entropy loss function at the end of our neural network, calculate gradients through it with respect to the weights of the network, and then use those gradients to move the network in the right direction. But with Pulse, we reverse that. We already have a pre-trained GAN. And theoretically, something you could do is if you already have an image and you want to know where that image lies within this GAN's manifold of different images, well, you find the gradient of this function, loss function, with respect to the input to the network. The input is your latent vector. So you start off with a random point in space, you have your final resulting face that you know you want to find, you calculate the gradient with respect to the input, you iterate, you optimize, and eventually you find out where your face is located in that vector space, in the latent space. Now, imagine this. Downsampling is technically a differentiable operation because it's really just averaging a bunch of pixels. And so, what if you had an already downscaled image? Let's just say a 32 by 32 image. It lacks a lot of detail. Now, because it has fewer pieces of detail or fewer pieces of information than a 128 by 128 image, it's always possible that multiple different 128 by 128 images can map to the same 32 by 32 image. That's why it's impossible to go from 32 to 32 to 128 back to the original image, because there are multiple different images to map to. Regular neural networks would try to average these, and that's why you get weird blurring and smoothing, and why upscaling has never really worked in the past with neural nets. But this technique is different. Because they're using a GAN, they can actually precisely find a point within that vector space, that latent space, and they can tell the neural network to generate at exactly that point, so it can hallucinate exactly the details that it needs to hallucinate. They may not be the exact same as the original image, but they're close enough. Now, as I mentioned, because downsampling is a differentiable operation, what does that mean? That means you have an input of a downsampled image, say 32 by 32. Your neural network starts off with a random latent vector that is fed into the network. You get a 128 by 128 output. You scale that down. That's differentiable. That's part of your graph of operations now. You calculate the loss based off of what you know you are expecting from that downscaled output. Then all you do is you calculate the gradients with respect to the latent vector, and you optimize that input over and over again until you find a latent vector whose output, when downsampled, is nearly equivalent to the input to the model. That is really a pretty genius way of upscaling images, because it forces the network to hallucinate exactly the details that it wants to hallucinate instead of having to average out. But here's the thing, Pulse is pretty complex, and if you take a look at the PyTorch codebase, you would notice there's hundreds of lines of code. It can be difficult to go through, and it's difficult to really understand the way it works through code. So what I've done is I've gone ahead and boiled that down to approximately 20 lines of TensorFlow 2.0 code. And what that enables you to do is load in an entire generative adversarial network, use the generator in order to generate images, and implement Pulse at the same time. And so now, without any further ado, let's take a look at how you can implement Pulse in TensorFlow 2.0. All right, let's dive right into the implementation. Now, as you can see, I'm currently on my Mac, but this is pretty compute intensive, so we're going to need a GPU. So what I'm going to do is I'm going to SSH into a server that actually provides us with GPU power. Now, this specific server has 2 GPUs, but we're only going to be using 1, and we're only going to be implementing on a batch size of 1. Technically, you could scale up the batch size and get a free performance increase, but we're not going to, because we're only going to be working with a single image in this in this case. And so now what we're going to do is we are going to go ahead and exec into a Docker container. So I'm going to go into VI mode and exec into my Docker container. And this Docker container is a TensorFlow image, and so this does, of course, still support GPU access from within the container. Now, within this container, what I'm going to do is I'm going to open up a little Python file that I've already got set up. Now, this Python file is great because it only has 4 imports: TensorFlow and TensorFlow Hub, as well as NumPy and Pillow. Now, after we've taken a look at those imports, as you can see, I've also just got a very simple function called showImage. Basically, what this is going to do is it's going to take output from the model, and it's going to convert it to a pillow image, which can then be saved to the disk or shown to the user. Because we're SSHing into a headless server, it's going to need to be saved to disk, then transported back to my Mac. So let's take a look at what we do in this function. Basically, the output of the model is really simple. It's just the regular image output, except instead of it being on a scale of 0 to 255, so an 8-bit unsigned integer, it's from the scale of 0 to 1, and so it has decimal value, so it's a 32-bit floating point value. Now, this is because, of course, neural network operations wouldn't really work with 8-bit unsigned integers, and so we have to use floating point values. However, after you basically just multiply all the values by 255 to rescale, convert it to 8-bit integers, you can simply call image.fromArray, and it converts it to an image for you. Now, this line of code over here, this one really makes the program special. It's basically loading in something called a progressively growing generative adversarial network. It's by NVIDIA, and this ProGAN, as it's called, is basically going to enable you to use really high fidelity image synthesis algorithms. Now, what does progressively growing mean? Basically what it means is the generator and the discriminator are trained in an incrementally sort of resolution, sort of incrementally increasing method. And so we'll start off by generating just 8x8 images that don't really have any faces in them, but give the GAN an approximate sort of estimate of what the final manifold is going to look like. Then we keep those layers and add on a few extra layers to the generator and the discriminator that goes 16x16. And then we go 32x32, and in between we keep training until we're good at each of these levels. And then we continue to add layers until we get to say 1024x1024, and suddenly we've got super high fidelity images. And so the neural networks work in this way because it's a lot easier to train the GANs when you can do it progressively rather than all at once 1024x1024. And so NVIDIA had some really great innovation with that. Now the next thing that I'm doing is basically just a little bit of code sort of structure. I'm just defining a small constant called RD, so resolution downsampled. Currently it's 32x32. And so what that means is we're going to feed into the network an image that is only 32x32 pixels large, and we're going to expect that the network will help us upscale that from 32x32 to 128x128. As a matter of fact, on screen right now, you're actually taking a look at just some of the samples of what this exact code that you can go ahead and download from GitHub right now has already generated. It's really fascinating, and I'm going to show you actually running this code now, how it works, and how you can generate your own images too. Now, from there, I've got 3 lines of code, and these actually work with TensorFlow. So what I'm doing is I'm first of all starting off by generating what I mentioned as the random point in the latent space that tells the GAN where to generate. Now, this is not a necessary step. I really want to highlight that. These 3 lines of code are what they're doing is they're telling the GAN to generate an image. This is just so that we can get an image of a face. If you would like to, you could take a picture of your own face and scale it down to 32x32 and feed it into the down image variable. So instead of having these 3 lines of code, you could just have down image equals image.load and then your own image. You could very easily do that. However, for the sake of this example, what I want to do, just so that you can get an idea of how these GANs work, is actually generate an image using the GAN, cut it off from the network, so that's no longer part of the operational graph. So it's its own standalone image. Then load that back in through down image as a downsampled image. Pretend we don't have the high resolution copy and try and hallucinate a high resolution copy. So let's go ahead and continue keeping that assumption in mind. Now, what I go ahead and do, just so that we have some ground truth, is I save both the real high quality image 128x128 as well as the downsample 32x32 image to the disk as real and down.png respectively. From there, I go ahead and generate another random point in the latent space, in this case 512 dimensions. Why exactly do we do that? Well, remember, we want to optimize. So what we're doing is we're starting at, again, some completely random point in that space, and now we're going to use the power of gradient descent and TensorFlow in order to help us optimize this prediction to get us as close to the original value as we can possibly get it to be. In an ideal world, after the next few lines of code, pred coordinate, so the prediction coordinate, will be exactly equal to the real coordinate. Then again, we don't live in a perfect world. We have friction, and so it's not going to be exactly there, but it's going to be in the vicinity. Or, and this is completely a valid option, there could be another local minimum that's close enough to this original image, closer to where the actual next random point was in the manifold. And so we can't really say exactly what's going to happen because it's stochastic, but for what we want is the output, and so we don't really care what the latent space vectors are. So now what we do is we actually have the main loop of the program. In this main loop, what we're doing is we're starting off by defining a TensorFlow gradient tape. Now, a TensorFlow gradient tape is essentially a data structure that is going to watch different variables. And when it watches these different variables, what you're able to do at the end is you're able to tell TensorFlow, all right, you've been noting down the operations that I've run on these variables. Now, here's my output value. Can you help me determine the gradients with respect to whatever variables you've been watching according to the function that you've written down on your tape? And so, for example, in this case, what I'm doing is I'm creating a new TensorFlow gradient tape, and I'm telling it, watch the predicted coordinate. And then after I tell it, watch it, then I go ahead and feed that coordinate into the model. I then go ahead and take the output of the model and downsample it to 32 by 32. Because remember, we want the downsampled images to look the same, and by proxy, the high quality images should be somewhat similar. Then, after resizing, I calculate a loss value slightly different from what the Pulse paper originally used. Essentially, what this is going to do is we're going to take the absolute difference of our target and what we actually are currently predicting, and we're going to calculate the mean of that across all pixels. Then after we have the loss, I can go ahead and print that out. That's just housekeeping. But then from there, I go ahead and tell the gradient tape, hey, you've been recording all the operations I ran on that tensor. Now I have this final loss value, and can you give me the gradients with respect to the predicted coordinate? And with that gradient, we now have a vector that is pointing in the direction of steepest ascent. And what do we want to do? We want to do gradient descent. And so we multiply that gradient by negative 1.5. Why 1.5? Why that magic number? Well, it's because, traditionally with machine learning, we'd have a learning rate. And that learning rate is to stabilize training by making it so we don't take too many big steps in a single direction to avoid overshooting something. But in this case, the gradients are so small that we actually have to amp up the gradients. And so I'm actually multiplying by negative 1.5 to amp up the gradients a little bit, to train a little bit faster. But at the same time, it has to be negative so that we're pointing in the direction of steepest descent and not ascent. I then go ahead and add that to our predicted coordinate, and then I check simply. If the loss is less than 0.035, which is the sort of target threshold of quality, then we break. If we wanted the images to be even further high quality, we could really want this loss to be as low as we wanted it to get. But even this takes quite some time to compute on an NVIDIA Tesla P100 GPU at only 128 by 128. So I would say that this is a very achievable target for something that's not production, something that doesn't need to be pushed to production. And then what I just go ahead and do is take that final computed predicted coordinate, feed that into the neural net, take the output, and save that to the disk as prediction.png, pred.png. Now that we've got our 3 PNG files, it's time to take a look at some results. But first, we've got to actually run the code. So I'm going to go ahead and quit Vim. Looks like I made a change, so we're going to have to quit and write as well. So now what I'm going to do is I'm just going to quickly run python pred.py. Well, not Python 3, Python, because TensorFlow Docker image comes with Python 2. But if I go ahead and run this, what's going to happen is it's going to initialize a few things. It's going to take a look at the GPUs, make sure they exist. It's going to initialize CUDNN, the CUDA Deep Neural Network Library, and off it goes. As you can see, you can take a look at the loss value per iteration. It's printing it out. And at first, you're going to see some sort of larger jumps in loss going down. Over time, it's going to slow down. That's just natural in the sense that as you get closer and closer to what you actually want, first of all, there's a lot more jittering happening because remember, multiple different initial inputs can result in the same downsampled vector, and it's very difficult to compute those differences at that small scale. But another thing is that just generally as you get closer, you sort of start to plateau in the gradient space, right? It's not as steep, and therefore you're not taking as big steps, and you have to take very, very small steps at the end. That's also why we want to amp up the learning rate. But again, I don't want you to have to watch paint dry, so we're gonna speed up this clip, and I'll be back in a minute or two, right as we reach our target loss. I'll be right back. Alright, so as you can see, the neural network has just finished its whole optimization procedure. TensorFlow has ended the program, and now let's take a look at what our results actually look like. So what I'm going to do is I'm going to quickly remove the previous prediction and then zip up all of our PNG files into a single zip. Then, of course, because we're doing this on an external machine, I'm going to go ahead and copy that over to the actual host machine that Docker's running in. And then I'm going to go ahead and run a secure copy. And so we're going to do root thread zip to my home directory. So from there, we're going to go into Finder, if Finder ever loads up the new file. Oh, does that not work? Do we need to do ch flags no hidden thread.zip? Let's see, there we go. So now what I'm going to do is I'm going to go ahead and unzip the file, and let's take a look at what we uncover. So as you can see, even just from the thumbnails, before I open it up, you can tell that there's definitely a resemblance between all three, but just how far does that resemblance go? Well, let's first of all start off by taking a look at the real image. Now this, in and of itself, is pretty remarkable, right? The fact that we can generate such a wonderful fake image of a person is just really incredible. This human doesn't exist, right? That's literally the website, thishumandoesnotexist.com. And now we've actually been able to generate a face locally. Now let's see what happens when we take a look at a similar face, but very much downsampled. All right, as you can see, we have a very pixelated version of that face. You wouldn't want to put that in a presentation or anything of that sort. But now, what if we wanted to upscale that same image? Well, let's take a look at what that result looks like. Oh wow, that is actually really incredible. That's one of the best results I've gotten from this network so far. Wow, that is really close. Take a look at that. So what happened was, now remember, we have this ground truth original image, right? We know what this looks like. But the thing is, the neural network doesn't have that image. The neural network doesn't have this ground truth sample. The only thing that the neural network sees is this super weird pixelated face. And what the neural network, again, is trying to do is it's trying to generate a latent vector for the GAN, such that when you take the output of the generator and you downscale it similar to this super pixelated image, the two downscaled versions look the same. And once again, by proxy, that means that the super high resolution versions should look similar as well. You can actually take a look at some of the features here that look super similar. The facial structure, of course, is incredibly similar. The hair is pretty much exactly the same. It's the lighting. It's really incredible the way this works. As a matter of fact, if I actually probably go ahead and in preview resize this to 32 by 32, and if I go ahead and scale up, it should be pretty difficult to tell the difference between the two downsampled images, because remember, the GAN was actually trying to optimize the input once again, such that the two downscaled versions of the images look the same. As you can see, they look essentially exactly the same. There's some differences, around the eyes. You can see these 2 pixels over here, around, in fact, I think that's the only noticeable difference apart from the hair over here. But by using this technique, we've been able to upscale a face without using the, traditional methods like variational autoencoders and UNet and these sorts of things that introduce their own sort of smoothing and noise into the actual solutions. GANs are really incredible, really flexible architectures. I will say they're very, very picky about the way they like to be trained, because, you've got 2 competing neural networks. That is inherently a very difficult thing to actually stabilize. However, there are going to be more tutorials on this channel in the future regarding how exactly you can do that. And so thank you very much everyone for joining in today. I do hope you enjoyed today's tutorial on the pulse system and how it works. Now if you do have any questions or suggestions, feel free to leave them down in the comment section below and I will definitely get back to you. This code is already on GitHub and the link is in the description below. Apart from that, if you do like this sort of content and want to see more of it, please do make sure to subscribe to the channel and turn on the notifications so you're actually notified whenever I release new content. And without any further ado, thank you very much everyone for joining in today. Hope you enjoyed. Goodbye.